Whether the screen is visible to all of you?
Yes, sir.
Okay. Okay. Now let's start. So in our last class, we have started our discussion on Gann diode, and I told you just I shall take only 3 4 minutes time to recapitulate what we had discussed in the last class because the last class was held maybe 14 days back. But anyhow, so there I told you that the Gann diode came later, but before that, in the year of 1961-62, three scientists, their names were Ridley, Watkins, and Hilsham. They were done through some study on compound semiconductor devices, and in course of their study, what they have found that in case of your compound semiconductor like gallium arsenide, indium phosphide, they have multiple values in the conduction band. That means in normally in our elemental semiconductor, say silicon or germanium, you will find the valence band and the conduction band. Both the bands are there, but conduction bands have only one level of energy, though it is discrete in nature. Probably our director sir has gone through that from the 2020 model or some of the theory. Probably he had explained it. It is discrete in nature, but it is only one value or only one conduction band is there. But in case of your compound semiconductor like indium phosphide, gallium arsenide, the multiple values are there in the conduction band. And what they have observed is that the, in these different conduction band values, there is some energy kappa differences there. And when a very small amount of voltage or electric field is applied across the material, the outermost electrons, that means which are there in the conduction band, they are getting energized from there. They are getting energy from there and will move from lower value of conduction band, that means the energy band which is at the bottom, to the upper value. From lower value of conduction band to the upper value. Am I audible?
Yes, sir.
Okay. From lower valley to the upper valley. And the process what they have observed that was termed or they have kept the name as the transfer electron effect. And afterwards, based on their this particular study, the devices which were realized, say for example our gun diode, these are called the transfer electron devices. And the most important thing is that the gun diode was, and I can show you the what we had discussed in the last class. This is your the energy band diagram of gallium arsenide, and you will find a similar type of diagram from other compound semiconductor. But what is the point of our interest is that the conduction band value. That means you will find instead of one conduction band value, there are multiple values are there. Here at least two are there, and the difference between the energy level between these two conduction band, the bottom of the two conduction band value is 0.36 electron volt. And now, as I told you, based on this idea, Kant has developed his diode, and according to his name, the name of the diode came as Gann diode. But it is not that all the semiconductor device, from all the compound semiconductor device, from where the Gann diode can be realized. Though Gann has realized the diode only from one semiconductor material, that is gallium arsenide. But later on, other scientists they have developed the Gann diode using other compound semiconductor material, that is gallium arsenide, phosphide, cadmium telluride, zinc selenide, etc. And as from the history of the development of Gann diode, the Gann diode was developed by Gann in the year of 1963. But what I was telling that if you go through your the basic semiconductor physics, what our director said is going to cover, then you will find that there are thousands and thousands compound semiconductors are there. Either they are the materials of group 3 and 5 or group 2 and 6. Now the question is whether all these compound semiconductor materials are capable to show this transfer electron effect, or using them the Gann diode can be realized. one word answer is no. Why? Because it should not, it is not only the necessary criteria is there, that multiple values will be there in the conduction band, but at the same time, few conditions which are called the necessary condition for gun effect that are to be satisfied. So number one was at least two conduction band values with energy difference delta E greater than KT0. Delta E means that is the energy gap what you have seen here 0.36. And why KT0? K is actually Boltzmann constant and T0 is the room temperature in absolute scale. So therefore, as it is not zero, that is generally, I told you in the last class, 27 plus 273, we generally consider as 300. So 300 into this value of K, that will give you the energy of electron at that temperature. That means electron can gain energy from heat, but even from room temperature, they can get some energy. I'm not get very large amount of energy because KT0 is not a very large value, but its value is less than 0.36. And I told you why it is required, because if it is not so, that means if KT0 is more than that, then at room temperature, the electron transfer effect will start. I hope that you can understand. No need for any external voltage or field. From energy, the electron will gain from room temperature, and with that energy from there, the electron transfer effect will start. So that's why one of the necessary conditions is that the KT0, that is energy gained by the electron at room temperature, must be less than the energy gap between the two conduction band values. Number two, this is number one. Number two, I told you here the electrons in the lower valley of the conduction band could have low effective mass and high mobility. And we will discuss because we have done through mobility. Mobility is the actually that tells about the velocity of electron under electric field. So it is the drift velocity per electric field. So therefore, the mobility is very important for movement of electron at the same time mass. Because if the mass is very large of any body, then it will be difficult to lift it up. So that's why if the mass is very small, then electron can easily move from one energy band to another. That's why this comes. But we'll prove this second relation or second condition mathematically. I'm coming into that. What we mean exactly, or what is the meaning of the this particular sentence, what I've written under condition 2 exactly, I'm coming into that. And delta E, that means the energy gap should be less than Eg. That means this energy here, this is delta Eg, the band gap energy. Delta E should be less than that. Otherwise, what will happen when because this whenever you apply voltage into charge is the energy. So with that energy, electron will transfer from valence band to conduction band. Valence band to conduction band, breakdown will occur. So that's why these two conditions are very important. So now I'm going to prove these two conditions mathematically, but just I want to take 3 minutes break from you. Just I'm coming from toilet and just 3 minutes. You wait for just 3 minutes, and I'm coming back within 3 minutes. Sorry for the interruption. So what I told you that these are the three required conditions, and I am going to explain condition 2 and 3 again after some mathematical analysis, which I am now going to do. But one thing is clear that uh, later on again I will mention that every compound semiconductor material, every compound semiconductor material cannot satisfy or may not satisfy these three conditions. So that's why from every compound semiconductor material, the Gand out or fabrication of Gand out or Gand out effect is not possible. So that is a very fundamental question. Now, as I told you, we are going to see what we mean by the transfer electron effect, or here also one more thing we will prove that I told you probably you can recapitulate in our earlier classes that in all these devices, that means we have done through impact diode already, and then we are discussing with gun diode, and maybe after that we will go through tunnel diode. So you will find that all these devices, they have one common feature, one common characteristics, that is they all are negative resistance device. They all are negative resistance device. And I told you what is negative resistance, but I have not explained clearly that what is the significance of negative resistance. Maybe in some other class I will do that today. I will not find time to go through that. But before I go to tunnel diode, I shall explain what is the utility, what is the significance of the negative resistance. But negative resistance means I hope that you can understand for normal conductor or resistor where when you increase voltage, current increases. That means change in voltage and change in current, if you consider, both are positive. That means if you increase voltage, current also increases. So that means if you take the ratio from the slope of the graph, what the voltage versus current characteristic, you will find it is positive. But in case of your these three devices or some other devices which are there, you will find that with the increase of voltage, current decreases. With the increase of voltage, current decreases. That is a peculiar phenomenon. So that's why if you take the slope, then delta V means increase in voltage means 3 to 5 volt. If you increase or 5 to 7 means change is positive. But if you go through current, you will find it is coming down from 7 to 5, 5 to 3 in that manner, in milliampere say. So 3 minus 5 means minus 2. So that means now if you take the ratio of delta V by delta I or V by I, you will find it is negative. So that is how it can be negative. But I also told you that negative resistance is a common feature, a common phenomenon of all these devices, but mechanism that how the negative resistance develops will be, because it is the inherent property, what I am going to tell you here also. It is the inherent property of the material or of the device by which they will develop the negative resistance. But this is not like your normal resistance which you can design considering the length or cross-sectional area of a conductor. That means you know that R equal to O into L by A. So by increasing area or by increasing length, by if you increase length, resistance increases, if you increase area, resistance decreases. So that always know from your HS classes. But that formula is not valid over here. So that's why here it is a negative resistance device. But how here in case of gun down, this negative resistance is coming. Now I'm going to tell that. But in order to go through that, in order to analyze that, we have to go through this mathematical analysis. And here actually, uh, I have considered three parameters of a material. Number one is the mass of the charged particle within the material, their mobility, and their number. So if you consider, as I told you, there are two values, as you have seen in case of your gallium arsenide. One value is there, and little bit above that, another value is there. So that's why the first one, if I go back to that figure diagram, then it will be easier. So this value is called lower value as it is marked over here, you have noticed, and this is called upper value. So I am going to consider the mass of the electron which are here in the lower value, say mass m suffix l, mass of electron at lower value, their mobility as mu l, and the number, that means number of electron presence in the lower value, say nn, nn. And Similarly, same for upper value as mu, mu u, and nu, because u, the suffix u stands for upper value. You may ask that, sir, whether this electron concentration or electron numbers, what you are considering NL or Nu, whether they are variable, actually the total number of electrons in the conduction band. I hope that you have read it, you know it now. Total number of electron presence in the conduction band, that depends on number of impurity concentration. That I told you earlier, that if you dope with one impurity material, that means in case of say N type, if you dope with one phosphorus atom, then one you will get one free electron. For two phosphorus atom, if you dope with, you will get two free electrons. So that means your number of free electrons in the total in the conduction band, that depends on total number of impurity atoms per cubic centimeter of the crystal material. Per cubic centimeter of crystal material. So here the total number of electron is fixed. When you have doped the material, it becomes fixed. That means N is fixed. But the distribution of these electrons, that means this is the conduction band and these are the two energy level of the conduction band. So some electrons or most of the electrons will be there in the lower value of the conduction band, and few who have got some energy or maybe they have a little bit more energy, so they will be there in the upper value. Or maybe in the lower valley it is completely filled, upper valley maybe complete. It depends on the energy distribution. So that probably director sir will discuss how this energy distribution or how this actually the number of electrons, how many number of electrons will be there in lower or upper, that will be decided by the energy gained by the electrons. But now what I was telling, I'm going back to there. So that means here we are considering the mass, mobility, and number of lower value electrons as ml, μl, and nl respectively, and same for the upper value as mu, mu, and nu. So now let's start with that. So here then conductivity. I hope that in the meantime you have gone through the formula of conductivity. Conductivity, this formula can be easily derived, but as it is there in the portion of director sir, that's why I'm not going into that. Probably have gone through that. Conductivity sigma of any material, it depends on the three things. One is Q charge of the particular P charge or which is the presence there, then mobility, and then number of features. So sigma equal to NQ mu. Sigma equal to NQ mu. I hope that, or EQ mu if you denote the charge as E and mu. You can write if you denote charge as E. But here as electrons, as I told you, are not there in only in one conduction band. So that's why, considering the lower and upper value and their distribution, I have written that Q is the charge. It is common for every lower value and upper value electron because it's the charge of electron. But as the mobility and number of electrons are not same, so this is for lower value, this is for upper value. So Q ml nl plus Q mu ne. These are the total sum of the conductivity of lower value plus upper value, means the conductivity of electrons in the conduction band. And I have taken Q common as it is same for both lower value and upper value electron. So that's why this is your equation number 1. I hope that it is clear. I am going to ask you later. And now, as I told you already, N is the, if N be the total number of the electron presence in the conduction band, and I told you that depends on carrier concentration, and carrier concentration depends on impurity concentration. That means how many carriers per cubic centimeter, how many free carriers per cubic centimeter of the crystal will be there, semiconductor crystal will be there. It depends on the concentration of the impurity atoms. So that's why N, which is sum of NL plus Nu, as just now I told you, and which is the total carrier concentration. And now, when electrons are accelerated, because just we are discussing about the drift velocity 2 minutes back, and I told you that when their electrons can move to any material in our semiconductor or semiconductor device physics, we have read it, that by two mechanisms electron can move. One, when there is a concentration gradient, that means in one side there is a large number of electrons are there, and other side there are few electrons are there. So because of concentration gradient, the electrons will move from maybe the large concentration area to the lower concentration region, and these mechanism is called diffusion. And these mechanism or this process continues till the equilibrium level reaches the concentration of both the sides become equal. But other case where there if there is one single charge or many charges are there, and if you apply voltage means electric field, then the charge failure, this electric field will exert force. I told you in my earlier classes when I had done purified diode that charge into electric field is the force. That force will be exerted by the electric field on the electrons. So as a result, they will move towards from one end to the other end within the material, and that velocity is called drift. So here only electrons will move due to applied voltage of electric field. That's why the velocity of electron here we will consider as drift. So now what I was discussing is that when electrons are accelerated under high electric field, that means now we are applying voltage and we are increasing it, means voltage value or electric field value is gradually become higher and higher. Then due to change of effective temperature rises and the lattice temperature, because you know that when voltage increases, then current, when electron move flows means current flows, then temperature increases within the material. So that's electron density. That means electron will gain energy. Electron will gain energy from this voltage field, as I told you, and they will now, as they are gaining more energy, so they will jumps from lower valley to the upper valley, because upper valley electrons have the energy level which is more than lower valley. So as lower valley electrons have gains energy, they got energy from the applied electric field or from the temperature that rises within the material. So automatically they will jump to the upper valley. And that we have discussed in our initial part of our this particular topic, which is called the transfer electron effect. Thus, electron density n and mobility mu both are the function of electric field. Both are the function of electric field. I hope that you have gone through the definition of mobility. That is the drift velocity per electric field. That is the drift velocity per electric field. So therefore, now let's see how mobility varies with electric field and how this your total number of carriers, their distribution depends on electric field. Distribution means from lower valley, they will transfer to the upper valley. So as a result, the lower valley electron number will decrease and upper valley electron number will increase. It's a very easy thing to understand. Initially, maybe large, I told you, large number of electrons or most of the electrons are there in the lower valley. But when the transfer electron effect will start, then automatically the number of electrons in the upper valley will start to increase, and as a result, the lower valley number of electrons will start to decrease. So let's see how due to electric field or what is the relation with this electric redistribution of electron numbers and the mobility that we are going to discuss in the next slide. So here what I did is that first is that I am just going to take the differentiation of this sigma, that is the conductivity, with the electric field E, with the electric field E. Now, why I am going to do that, just I shall tell you a little bit later. Then it will be easy for you to understand why you are doing this. First, we just think that just by using simple calculus, we are going to make a differentiation of sigma with respect to electric field. Now, the question is, you can ask me, just said, how you come to know that sigma will vary with, because differentiation means where you want to study the change of one particular thing with respect to other. That means here we want to study the change of conductivity due to change of electric field. So now the question is that how I can, or some the scientists, they can come to know that this conductivity depends on electric field. It is very easy to understand, because you know that your the conductivity or resistivity, the conductivity and resistivity, actually that are very much related to this current or voltage. Why? Because here you know that whenever you apply or whenever you increase voltage, in general what will happen? In general, in a material, when you increase voltage, I am talking about normal material. Whenever you increase voltage, current increases, more current will flow, and automatically, as more number of currents will flow, then we can say the material conductivity is increasing, because conductivity that depends on the amount of the conduction of the charge or particle or flow of charge particle. So therefore, the conductivity depends on voltage or electric field, and now I am going to vary that. But I already told you the mu and n, mobility and the number of charge carrier, they varies with electric field. That is written in the last line. Both varies with electric field, because mobility definition that tells that it is drift velocity by electric field, and n, I told you, because of applied electric field they gains energy from electric field or voltage as well as from temperature, and as a result they will transfer, and their your electron concentration will change from lower value, that will decrease, and in upper value to increase. So that's why mu and n both varies with electric field, but whenever you go to differentiate, then as both are varying with electric field, so we have to run through the partial derivative method. I hope that you have read the partial derivative method in your calculus. So partial derivative method is that when both parameters are varying with respect to one, then to see that variation or change, you have to, when you differentiate one, then you have to keep other things. That means when you differentiate mu, d mu d, then n is fixed. And next time mu is fixed, we will go for d n d. So now we have followed that. That means in the next step, when we are differentiating sigma with respect to E, electric field, then we are going through the partial derivative method, and here you will see that. So Q is charge that is independent of electric field, so that's why it is outside, it is constant, the bracket or integration. Then I told you first we have kept mu constant for both the your lower value and upper value, and we have differentiated n with respect to dnl by d plus dnu by d. And now in the next step, I told you when you have taken difference from n with respect to e, mu was constant. Now we are going to differentiate mu with respect to e, then n are constant. I hope that this differentiation is clear, which is under your equation number 2. Is it clear to all of you what I told you? Any one of you? Is it clear? Am I audible?
Yes, sir.
Okay. Okay. So it's a very simple differentiation, nothing so difficult, or nothing is, there is no maybe not very difficult to understand. So I hope that you have understood this. But now, as I told you that here I'm going to just show you that if we now differentiate this number of carriers, upper value plus lower value, that means the total number of carriers in the conduction band with respect to E. With respect to E, that means dn by d, because I told you in your previous that you have seen n is nl plus nu. If you take dn by d, means dd of nl plus nu, that I have written over here, and that is equal to 0. Why 0? Because I told you total number of electrons in the conduction band, total number of electrons presence in the conduction band, that depends on the doping concentration. That depends on the doping concentration. That doesn't depend on the electric field. That doesn't depend on the electric field or voltage, because electric field or voltage can give energy, can accelerate them, but they cannot produce new electrons. So that's why here the dn by d, that is total number of electron concentration, as it is constant, it doesn't depend on electric field. So dn by d is 0. But at the same time, these dnu by d or dnl by d, they are not fixed, because you have seen, or I told you already, that is the transfer electron effect, where the electron will transfer from lower value to the upper value, and as a result, the concentration of electron that will change. Lower value concentration decreases with electric field, upper value should increase. So that we'll see in time. But anyhow, that dn by d is 0, but this part, if you consider equal to 0, then we can write dnl by d, that is equal to minus dnu by d. I hope that it is clear that as this is equal to 0, means dnl by d equal to minus dnu by d. And that is your equation number 3, and that equation 3 will utilize in the next part of our derivation. But now, I told you already, we want to see the dependence of mobility with electric field. So, if you run through your different research papers published by different research scientists, then you will find that mobility that varies with electric field. Initially, the I hope that data set has gone through that mobility initially increases linearly with electric field, but then ultimately when your electric field value is higher, then mobility saturates. That means mobility varies with electric field, mobility changes with electric field. But what is the relation? What is the relation between mobility and electric field? If we do not know, you have got to bother about that. If you do not know, you have to bother about that. If you consider anything, just mu mobility is proportional with electric field to the power T. Electric field to the power T. That means whether mu is proportional with E square EQ E4 or 1 by E square 1 by EQ, or we are not bothering about that. We are just considering mu is proportional to the power T, where T may be anything positive to negative value except 0. That is enough. P may be anything. For the sake of argument, if you consider if somebody tells that mu is proportional to E square, some tells that no sir, it is proportional to Q. I am not going to any type of argument like that. I am going to consider a simple consideration that mu is simply proportional with P to the power T, where P may be any value or anything positive to negative except 0. So then this P is a constant and have some value in integer value. And now if you now differentiate mu with respect to P, so you know that d mu by d, if you write d mu by d, if you differentiate mu with respect to electric field, then if you want to remove the proportionality sign, then you have to put equal to k into this. But the k is constant, that you cannot differentiate, it is a constant term. So that's why what I did here, I didn't consider any constant. I didn't consider any constant because if it is there or not, that doesn't matter in differentiation. Only if you differentiate with k, the k term will come before that. If you do not differentiate with k, then k will not be there that much. But differentiation will remain same. I hope that you can understand. So that's why if you write d mu by de, then it will come as p to the power p minus 1, because you know that differentiation of x to the power n is nx n minus 1. So p to the power p minus 1, that I have written in the next line. So p to the power p minus 1, it is here, if you follow my cursor. Then, and proportionality sign I am maintaining, because otherwise you have to write a k term here, I told you already. And now, if we write this p, and if we write e to the power p by e, because it is e to the power p minus 1, so we can write as e to the power p by e. So then, in the next line we can write as the proportionality of k into e to the power p means it is mu already. So I'm just going back to that our old relation, because if the k is there, then k into e to the power p, which was initially mu. So that mu I have substituted here. So ultimately we are getting d dE of e to the power p is equal to p mu by e. That is your equation 3. So I already told you we'll utilize this equation 3 as well as equation 4 in our next part of our derivation. So just we are going to substitute this relationship in your equation 2, this equation, in equation 2. So let's see. So d sigma by d, your equation was on the left side, equal to q mu l dnl by d plus mu dnu by d. But you have written dnl by d equal to minus dnu by d. That means in place of dnu by d, if you write minus mu into dnl by d, there is no problem, and we can take dnl by d common. So that means in the next step we will find here it is coming as q into dnl by d, because this is your dnl by d also as per equation 3, and then within bracket mu l minus mu, within bracket mu l minus mu, that I have written over here. I hope that it is clear. And for the next part, as I told you, q into nl d mu it by dv is, you have just seen now, the p mu e. So p by e I have kept outside, and this mu I have written as q into mu l nl plus this, because as we are differentiating, mu is coming back, so that means I have written here, this p by e I have taken outside. Okay, clear? So that is your equation 5. Now, this is another relationship. Can any one of you tell that from where we can get this relation J equal to sigma E? You know this relation, have you seen it ever? The current density J how it relates with conductivity and electric field, J equal to sigma into E. Whether you have seen this relation earlier or from where it is coming, do you know? Anyone, if you know,
Yes,
you
sir.
can tell me. Yes,
Microscopic Ohm's law, it was something like that.
yes, it is also an alternative, or maybe you can say that is another way to represent the Ohm's law. Very correct, because it is very simple to find got this expression. Your Ohm's law generally write V equal to IR. So in place of R, if you write rho into L by A, and that L if you take to the left side below V, so V by L is your electric field, and on the right side, it is then rho into as your relation was I by A. I by A is your current density J, and if you take the rho on the other side, that means in towards where the E is there on the left side, now it is E because V by L. So 1 by rho it is coming on that side. So 1 by rho is your sigma. So J equal to sigma E, that is another form of Ohm's law. So now why we are considering that and why we have started our discussion or rather derivation of sigma with respect to electric field, now you get the answer here. Because here we want to see that if your d sigma d or dj by d, this value is negative because dj means that is related with current and E that is related with voltage. So dj by d means it is indirectly di by dt. If you remove the parameter of the device, that is cross sectional area or the length, then it is simply I by V. So therefore, if it is negative, then we can say it is a negative resistance device, because I just told you with the increase of voltage, if current decreases, dV di, if you take the relationship and if you write di by dV or dV by di, if it is negative, then that is the negative resistance device. So therefore, J equal to sigma E, and we have taken differentiation of J with respect to E, because I told you our objective is to see whether dj by d is negative or not. dj by d negative means di by dv is negative. So J then sigma remains constant, d by d minus 1 plus E, then differentiation of d sigma by d, because sigma is varying with electric field. And now just simple mathematical manipulation. We have divided both sides of the equation by sigma. So it is coming on the left side as 1 by sigma djd, as I have written over here. Then equal to 1 because we are dividing by sigma, plus E by sigma this. But in place of E by sigma, I have written divided by sigma by E. I hope that you have no objection. D sigma by D into E by sigma, plus in place of E by sigma, I am going to write sigma. Now, as we have mentioned earlier that negative resistance, the current density or current should be negative or should decrease with the increase of voltage or electric field. So our objective is to see whether djd is negative or not. djd negative means its value should be less than 0. djd negative means what? Its value should be less than 0. So that I have written in the next line. So that means djd is negative means it is possible only when the right hand side equation 6 is less than 0. Because if this is less than 0, this is the same thing, 1 by sigma is there, then djd is less than 0 means the device is negative resistance. So that I have written here. So it is negative means this is less than 0. The part which is there in the right hand side, that is less than 0. Sigma plus E d sigma d, that is less than 0. Or minus this thing, yes, using the condition of inequality, minus d sigma d, this is greater than 1. So that is our equation number 7. So now once again I am asking that anyone please tell me whether it is clear to all of you or shall I repeat it again? Anyone please
Yes,
tell
sir,
me.
it was clear.
Okay. So then we can move to the next part of our discussion. So up to equation 7, it is clear to all of you. So now the next thing is that d sigma by d, that already we have derived, is equation 5. Equation 5. And here, then in the denominator it is sigma by e. Equation of sigma is there as equation number 1. Yes. So that if you divide both sides by E, if you divide both sides by electric field E, then it is coming as, as I told you, it is coming as sigma by E. So therefore, in the next step, we have to substitute that. That means d sigma by d, d sigma by d by sigma. That means equation 5 by equation 1. Dividing equation 5 by equation 1. What we are getting? We are getting this one. This one. Okay? And now, just we are going to write nu by nl, because here from here we will take nu common. We will take sorry, nl will take common. NL will take common. So nu by nl, that we are going to transfer at any instant of time. DC, because I that with the application of voltage or electric field, the concentration of lower value electron will change, and that means decreases, and upper value increases. That means this NuNL value will gradually changes with electric field. But at any instant or at particular value of electric field, that value is a constant Nu by NL at any moment. So that is your key. And multiplying, oh sorry, there is one spelling mistake. Multiplying both sides by E, because I told you dividing by E or multiplying both sides by E, ultimately that E will come here in the denominator of sigma. So multiplying both sides by E, we can get this. That means from this step to this step we are getting. And I already told you what is P and what is K that I mentioned. P is any integer. When we have considered the mobility and its proportional with electric field, it is the power P. This is your K. So this is our the next step of derivation, and then final step from equation 7. From equation 7, then what we can write, because I told you that as this thing already we have considered in your previous equation 7, this thing minus this thing should be greater than 1. That means if as minus is already there, or rather I have taken multiply both sides with minus, so that I can utilize that condition minus d sigma by de, sigma by e greater than 1. What I did, I am repeating once again. In the next step, we have divided e, that e we have multiplied on both sides, then divide that e I have written here as sigma by e, and I have written minus on both the sides. So d sigma by d by sigma by e, which was there here, that should be greater than 1, means your right hand side equation, this equation must be greater than 1. Your this right hand side must be greater than 1, because this left hand side should be greater than 1 as it is equation. So right hand side must be greater than 1. So that I have written in the next slide as equation 8. So now let's see, and what I did in the next step, this minus sign I have taken inside. Actually I have written minus here as minus dnl by d. In the next line you will see, and minus p. This minus will, when enter within the third bracket, then it will be multiplied with the first part of the this factor and with the second p also. So minus dnl by d minus p, that I have written here. Minus dnl by d with minus p, and now it is greater than 1. This is just maybe you can say a jugglery what I made over here, just minus and I have written here and minus sign here, and so that I can write now it is greater than 1. Now to maintain the inequality of this equation 8, what we have to do? Actually, first thing is that this whole thing, how this third bracketed term can be greater than 1, how this third bracketed term can be greater than 1, if the first part, that means those which are there under first bracket, the first part of the expression is greater than p, then the whole thing can be positive and can be greater than 1. See, in order to make this thing positive, what are the necessary conditions are required? So I already told you that if mu u is less than mu l, then it can be positive. Otherwise, if mu u is greater than mu l, then negative sign will come here. And that negative, I'm coming here, you can say, sir, what will happen then? I'm coming. But one necessary condition to make this term positive, so that the whole first bracketed term here be positive and greater than P. So first condition is mu L must be greater than mu U, so that no negative sign should come here. And other thing is that dNL by D, dNL by D, that itself should be negative. Why? Because I just told you that with the electric field, the concentration of lower value of electron will decrease and upper value will increase. So dNL by D, that is the change in concentration of lower value electron with electric field. That as it is decreasing means dNL by D should be negative. Then only we can say it is decreasing. So if dNL by D itself negative, then that negative and this negative, which is already there, makes it positive. And in that case, if mu is greater than mu L, then negative sign will come here, and which makes the whole thing negative. I hope that you can understand. As dNL by D itself negative, so that negative and this negative when multiplied, this first bracket term will be positive. And in that case, if mu U is greater than mu L, then a negative sign comes here, and that makes the whole thing negative, and automatically it cannot be greater than 1. So that's why mu should be greater than mu U. Mu should be less than, mu should be less than mu L. That means the mobility of upper valley should be less than that of lower valley. Mobility of upper valley should be less than lower valley. And dNL by D, that is negative, because I just told you that electron concentration in the lower valley that decreases with the increase of electric field. And now, as I told you, mu L must be greater than mu U, which was your condition number 2. If you go back to the condition here, it was there that I'm coming to the effective mass later. The lower valley of the conduction band should have high mobility than the upper valley or higher valley. So therefore, I hope that you can understand that mu L greater than mu U, that tells or that satisfies the condition number 2. And effective mass, I told you, probably many of you know what is effective mass. That is not the actual mass of electron, but when electron moves through different charged particles, so automatically it will have some attraction or repulsion effect with other charged particles. So as a result, their normal motion will be hampered. So that's why Einstein has introduced this term, that effective mass, so that we can compensate this velocity variation. Though the mass doesn't change, then how the velocity is varying. So that can be compensated with the terms of with that particular term of effective mass. And if I told you whether effective mass or real mass, anything, if it is less, then that is better. You know that when the mass is less means it is easy to lift. So electron can easy to move, because to move from lower value to upper value it needs lesser energy. So that's why this condition, which was your condition number 2, that is satisfied. And already I told you regarding this condition delta E, because if the delta E, that means your applied voltage of electric field is such that electron moves from valence band to conduction band, that means if delta is greater than that EG value, then breakdown will occur. Large number of electrons will come here, and ultimately the conduction band will be saturated and breakdown will occur. Large current will flow. So that is not the Gunn effect. So that's why this is the condition which I had explained already, because condition 1, if it fails, then Gunn effect will start at room temperature. And third condition I told you, this is the condition that tells that if your applied voltage is very high, then automatically, and if your corresponding electric field or the energy of electron is more than the band gap energy, band gap means energy gap between the conduction band and valence band, then large number of electrons will move from valence band to conduction band, and as a result conduction band will saturate, and automatically the carrier concentration will increase and large current will break down occurs. So that's why these conditions are essential. And now I hope that you can understand that here, in order to get this transfer electron effect, the multiple value, that means why compound semiconductor is required, because only compound semiconductor materials have multiple values. That means lower value, upper value, or any other value in the conduction. It is not like our elemental semiconductor that it has one value in the valence band and another in the conduction band. It is not like that. So that's why, in order to get this gun effect or transfer electron effect, rather I should say, compound semiconductor is must, and at the same, that's why in your viva people will ask you, "Hey, why gun diode cannot be realized with silicon or germanium?" Because they the silicon and germanium, the semiconductor semiconductor, they do not have multiple values in the conduction band. So that is written in the next slide. So now elemental semiconductors like silicon and germanium have only one value in the conduction band, and hence this effect is not possible. I hope that it is clear to all of you. And again, as the electrons have the lower effective mass and higher mobility than the holes, thus enter, because I hope that you can understand, mass of holes are much greater than that of electron. Whether effective mass or real mass, I'm not going into that, but in general, that all of you know, actually mass of electron is about 1875 times greater than that of electron. So I told you when the transfer electron effect is there, when electrons will move from lower value to upper value, so automatically the mass of electron is very much responsible for that. So in that case, electron is preferable than hole. And that's why N-type gallium arsenide is used, because I told you, you have read in your semiconductor physics that any semiconductor material can be N or P type depending on the type of impurity concentration or dopant. But here, another important question, any viva your teacher will ask you that why silicon, why not silicon or germanium? And the second question is why only N-type gallium arsenide, why not P-type? I hope that it is clear. So is it clear again to all of you? Is it clear to all of you?
Yes, sir.
Yes, sir.
You take your preparation, mental preparation, because you have a lot of vivas in your maybe 6 m, 7 sem, 8 sem, so that there people will ask questions randomly. Okay, so that's why don't forget this thing. Now this is your how the mobility is varying with electric field. Initially I told you mobility generally for any type of material, initially mobility increases linearly. But in case of your gun diode, when the gun action, the gun effect, that means the transfer electron effect starts, then obviously as we have seen that the mobility that as the number of carriers in the lower valley is decreasing, mobility is decreasing, because lower valley electrons have higher mobility. So that's why you will find the mobility is decreasing. Mobility is decreasing with electric field, and then when you will cause the actually, if you look to the graph, then you will find some threshold value of electric field where the mobility will reach to the peak value. Then it will decrease with the concentration of electron, as in the lower value it decreases, and now it will reach to the minimum. And then if we apply the voltage, why the mobility is again increasing? Because here after EV, after the valley voltage or valley electric field or applied voltage is so high, and instead of transfer electron effect, the breakdown, that means large number of electrons will now move from valence band to conduction band, and as a result mobility will again start to increase. So that's why this is the velocity versus electric field profile, which tells about the mobility, and mobility value is negative over the region where the device shows negative resistance region, where the current decreases, number of electron concentration decreases, because I told you the reason. With the increase of electric field or voltage lower value electron concentration, the current means the amount of charge that flows. So automatically with the increase of voltage, electric field, as the lower value electron concentration decreases, so automatically total number of current decreases, total amount of current decreases. And now this structure already I had shown you, because in the last class, at the end of the class, only few minutes were there, so I got a chance to show you this. But still, again, I am going to discuss that. This is the normal structure of gun diode. So here you will find this is the N epi layer, means actually how the diode is developed. Basically, I told you that there is no junction in this diode. In GaN diode, there is no PN junction or no metal semiconductor junction normally what is there in any other diode. But still it is called a diode. That answer I will give you maybe in the next class when I will finish this topic. But today only I can tell that how we can fabricate the GaN diode. Actually, the starting material is N plus. After I told you what is N plus, value of the carrier concentration is written on the right side. When plus means it is heavily doped, and electron you will find that the impurity concentration or electron concentration is 70 to 90. Yeah, between middle of that 80. So over the N plus layer, an N layer is grown. This is called the grown layer. This is called the grown layer. Actually, I told you that in 19 actually impaired diode was fabricated by Johnson and Lee in my last maybe earlier classes I told you in 1965, because before that this growth technology, how the device can grow, this technology or no machine was developed to grow. That means you can by today by using the epitaxy process, by using the molecular beam epitaxy machine, you can develop layer after layer, N, P, N, P, any layer after layer you can grow. But that machine, that technology was not there in 1958 when Reed has proposed impact diode. That's why I told you, probably you can recapitulate, that Reed diode was a theoretical diode, a theoretical structure because of the complicated nature, the P plus N, I, N plus nature of the structure. But here, GaN diode was developed much later in the later part than 64, 65, that period. So that time this maybe in 1958 it was not there, but in 1960 or onward NB machine was there. Using that, N layer is grown over N plus, then another N plus layer is grown over N. Now I told you why on the two sides this N plus, because your active layer, what are the transfer electron effect or your this maybe electron transfer takes place from lower valley of conduction, but that takes place in N region. That is the N epi layer. But why N plus are there? Because if you deposit metal directly over N, that means why the metal layers are there, that I told you in your next semester when you go through microelectronics, that time we'll discuss it again. Because to get electrical contact from the device, you have deposited metal on the two sides of the fabricated device. Otherwise, you cannot directly solder a lead over a semiconductor, because lead is metal. Lead is made of metal and semiconductor is insulated. You cannot solder a metal over an insulator. So that's why you have to deposit metal first by some deposition technology on the two side of the fabricated device, and then you can solder lead over the metal. So here, that's where the metals are there deposited. But if you deposit metal directly over N layer, that means if the N plus layers are not there, then what will happen? Let's see. Then between the metal and this N layer, if you deposit metal here and at the same time on this side, I told you that between metal and semiconductor, because of the work function difference, because of the energy barrier that developed due to work function difference, you will find some diode action. And director sir will go through that. That is called the metal semiconductor Schottky barrier diode. So therefore, you will find one diode action here, and because of deposition of other side metal here on the N layer, you will get another diode action from this side. So that means you will find, instead of GaN effect, you will find it is a combination of two metal semiconductor junction diode. So in place of that, if you deposit N plus and N plus over N, I told you N plus means where the semiconductor have higher conductivity. So as a result, if you deposit metal over there, then because of the, as I told you here, the concentration, carrier concentration is very high. Here also metal is very large because large number of free carriers are available. So therefore, the barrier potential is zero nearly here. So automatically current can easily flow. So no diode action you will find over here. Maybe some resistance difference because of the carrier concentration difference, little bit resistance. So that's why this type of contact is called ohmic contact that I told you earlier. And if you deposit metal directly over N or P, then that is called the diode or rectifying contact. So that is why two metal layers are there. And now the equivalent circuit. So if you consider the N region, N region. So here I hope that you can understand, here N region or within this N plus N plus region, then you will find that it is a semiconductor material. Semiconductor is not perfectly conductor, so that's why you will find some resistance. That means when current enters from top and flows towards bottom, it will face some resistance due to the N plus layer. That is because of the semiconductor and its insulation or insulating nature. It is not perfectly conductor. But now, so that's why this resistance you will see here R, that is due to this. And now again, across the material or this semiconductor, there are two metal layers. You know that I told you probably in my earlier classes that when there are two metal layers, when there are two metal plates, when there are two metal sheets, metal rod, metal wire, separated by means of some free space. Free space means air or any other dielectric, rubber, plastic, or ceramic, anything. Then that gives rise of some capacity. Because the as the metal plates are separated, so charge carriers cannot move from one plate to other plate directly. So that gives rise, that means the charge will remain stored there, and that is the effect of capacitance. So that's why it will, due to these two metal layers across the N plus and N plus, you will get the capacitance effect and this. And now whenever you solder some, I told you, then you have to connect lead for external connection on the two sides of the metal. So because of the lead, because of its length, you will get some resistance and inductance effect that I told you in case of impaired diode also. So that series resistance and this inductance coming due to this packaging only. And finally, I told you, I had shown you that the particular type of package which we are using for impaired diode, the same type of package we use over here. The same type of package we use over here, and that is the export package. So whenever you encapsulate the device within the package, then due to the package or across the package, because package top and bottom, there is some metal starts and cap, and there is a ceramic layer at the center of the package that you have seen in case of impaired diode. So again, due to that, you will get some capacitance. So that is called package capacitance. So CP is the package capacitance that is coming across the device, and these are the your equivalent maybe resistance, capacitance, and inductance coming with the equivalent. And I told you, probably you can recapitulate that whenever you draw the equivalent, repeatedly I'm telling you in each and every class when I'm showing you the equivalent circuit, that whenever you draw the equivalent circuit, unless and until you write below that what is R, what is C, what is RS, what is NQ, you cannot get full marks. You should be careful about that. If you only draw the equivalent circuit, if 1 mark is there for that or 2 mark is there for that, you will get only 1 or half. So now we'll go through the modes of operation of the gun diode. So gun diode can operate in 4 different modes. One is called transit time mode. You can ask me, sir, what is transit time? I told you earlier. If you recapitulate, then you will find that transit time is, it is the time taken by the charge carrier to cross the active region of the device. It is the time taken by the charge carrier to cross the active region of the device. Therefore, when you have applied your voltage and when your charge carriers will start to flow with their normal velocity, or which is the 10 to the power 7 centimeter per second, that is the value of the maximum value of velocity Vs. Then actually I told you, if this N layer have the length L, if N layer have the length L, because that is the active layer I told you, then how much time electrons will take, or charge carrier will take to cross the N layer from this side to that side. That is called transit time. Because I repeatedly telling you, transit time means it is the time taken by the charge carrier to cross the active region of the device. So therefore now, if we consider L be the length of the active region, and Vs is the max, because I told you the drift velocity that varies with electric field or mobility varies with. So your drift velocity initially will remain constant as we have seen, and then that generally saturates as mobility saturates. So therefore we are going to consider the maximum drift velocity, that means drift velocity at saturation, Vs. Then L by Vs. L is the length and Vs is the velocity with which charge carriers are moving. So L by Vs is the transit time. So when your applied voltage or electric field is such that the charge carriers have attained the maximum saturated velocity and moving through this NAP layer or active layer of L length, then L by Vs, length by that velocity, is your the transit time tau. Or 1 by, as you know, tau means time means 1 by frequency. So 1 by f equal to, just to try to keep it in mind, tau equal to L by Vs. So 1 by f equal to L by Vs. So Fl equal to Vs. So Fl equal to Vs. That I have written here. And Vs, I told you, that is the value which is called the maximum or saturated. This value you will keep it in mind, because in many problem, in many problem related to device, people will not give you this value, or in your problem values will not be given. You have to put the value as and when required. Now, as here I told you the oscillation, that means automatically using this diode when you produce an oscillator or oscillation will develop. So then automatically the oscillation period is equal to the transit time period. That means tau, if tau 0 is the transit time of the device, and then t equal to tau 0, and that's why this mode is called transit time mode. That means, once again I'm repeating, I'm just going to maybe summarize the whole thing. Actually, I told you that it is the active layer, region, active length of the region in layer, and Vs is the maximum or highest velocity with which charge carrier can move. So automatically, the minimum time, that is the transit time taken by the charge carrier tau, is equal to L by Vs, and that I have written there. And now I told you the tau is 1 by f, so Fl equal to this. That I hope that you have understood. But now, why it is called transit time mode? Because under this mode, electrons are moving. Electrons are moving or taking time to cross the active layer, which is equal to transit time, which is equal to transit time. So that's why it is called the transit time mode. Generally, it is a low power mode and low efficiency mode. And in this mode, it has been observed that these are the reported value what I have written over here. It is a low power and low efficiency mode. And in this mode, the device operates up to a frequency of 30 gigahertz. Device can operate up to a frequency of 30 gigahertz. Now you can ask me, sir, whether electrons can move velocity lower than or higher than the transit time? Yes, I'm coming into that. Not by normal mechanism, but due to that. But here, when the electron moves with the time lower than transit time, that means what is the normal time that electron takes with the saturated velocity. So here the velocity is then less, then only it will take more time. So therefore, when the electron velocity is less, that means your electric field value or voltage is low. Electric field value or voltage is low because this field and voltage is responsible for this velocity. Vs or Vd, that is velocity, that value is electric field. So when the field value or applied voltage is low, then Vs or Vd will be low, then automatically your transit time will be higher, means frequency will be lower. And that mode is called delayed mode. So delayed or inhibited mode means here the oscillation, as I told you, the oscillation period is greater than transit time. That means your charge periods are taking more time. It is becoming slower, taking more time than the transit time, and that's why when they will move in the form of a domain or group of charge, it will take more time, and hence the operating frequency will be less, because time more means what is the frequency? It will be lower. That means in your previous mode, if you can operate at 30 gigahertz, in this mode you can go up to 10, 15 or 20 gigahertz maximum, lower than that. And also in this mode, efficiency is a little bit better than the previous mode, 20%. And now another mode is called the quench mode. Quench mode means which varies suppressed. That means it apparently looks like that the width of the N layer has reduced. That means maybe velocity will be a little bit higher than the saturation. So here the oscillation period is lesser because as velocity of the charge carrier will be a little bit higher, though we have considered nearly the saturation velocity. But as I told you that here when the electron transfer effect will start, the mobility that also decreases as we have seen. So here the velocity can increase a little bit, and as a result, the time taken by the charge carrier will be less than the transit time. So T is less than the transit time. So that's why in this particular operating mode, the device operating frequency is higher, because if T, the transit time is less, means frequency which is 1 by transit time will be higher, and efficiency is little bit lower, because the power efficiency, they are generally inversely related. So as you are getting higher efficiency, means more power, means automatically efficiency will be lower. And this mode is called quench mode. And now finally, the last one is the limited space charge accumulation mode, or LSM mode. In this mode of operation, that generally that is not the normal mode. This mode needs some extra additional circuitry along with the gun diode. That means it is not the normal mode of the gun diode which we are discussing. In our normal mode, we are just simply apply voltage. We have some experiment at our lab with gun diode, where our students, fourth year, when you are 7th sem, you have to perform that. You have to apply the voltage. You have to see how the charge periods are, maybe how the negative resistance is developing, etc., etc. But thing is that if you give some additional circuitry, design some additional circuitry, then using that, you can achieve this mode. That's it is written here. This mode of operation gives high power rise with higher efficiency. And in this mode, the operating frequency that is from 0.5 to 50 times, 0.5 to 50 times more than that of transit time. But it is, I told you, it is really very difficult to get higher frequency as well as at the same time higher power, because frequency power relation is always inverse. That always you remember. That means same device which is giving you maybe 10 watt at maybe 5 kilohertz. If you operate at 7 kilowatt, 10 watt will come down to 7 watt or 6 watt. So when you increase the frequency, the same device will give lesser power. But the only advantage is that in this mode, and why then we will go for LSM mode, because in LSM mode, the gun diode can operate up to a frequency of 100 gigahertz. Up to frequency of 100 gigahertz. In other mode, that means in your quench mode, it can go up to maximum 60 gigahertz. In transit time mode, you have seen this 30 gigahertz. In delayed mode or intermediate mode, it is less than 30 gigahertz. In quench mode only, it can go up to 60 gigahertz. But in the special mode, limited space charge accumulation mode, it can go up to 100 gigahertz. But you just try to keep it in mind. I told you, still it is less than that of impact diode, because impact diode can operate up to 450 gigahertz till now, as it is reported. So 100 gigahertz is much lower than that. Now, applications of gun diode. Gun diode is frequently used as low and medium power, because I told you generally these diodes are used for generation of high frequency oscillation. High frequency means microwave, gigahertz range oscillation. It is not your normal low frequency oscillator which we have read in your, or you will read in your analog electronic like Colpit, Hartley, Bindrich, or phase shift. A lot of crystal oscillators, lot of oscillators are there, but they are low frequency. But here they are high frequency and generates or produces oscillation in the frequency of gigahertz or microwave range. It is used as a pump source in most of the parametric amplifier. So I'm not going to explain what is parametric amplifier, but why the name is such, because generally you know that you have just heard it, that amplifier can amplify the signal. It can increase the amplitude of voltage or power of any input signal. That means when your signal is applied to the amplifier, obviously its output voltage or power level will increase. Then it is called amplification. But here, in this particular parametric amplifier, apart from amplification, some other parameter of the device that can change. And here, in this parametric amplifier, it will not only amplify the signal, but as and when required, you can change the frequency of the signal. So that means your signal was at 5 gigahertz and it is amplifying, or your amplification was 10 or gain is 10. But you can, keeping the gain same, you can change the frequency also. So that's why as you can vary some other parameter of the amplifier like frequency along with amplification. So that's why it is called parametric amplifier, which is there in our 7th semester microwave syllabus. We'll discuss it there, because I told you application parts are mainly there. Here only we'll discuss about the device physics, principle, operation, equivalent circuit, etc. And palm source means in order to change these or for parametric amplifier application, another external source is required along with the internal source. So that is called palm source. So here gun diode can be used as a palm source. High power gun diode can be used as CW or continuous wave radar, because I told you probably radar is one of the most important invention. In my view, it is the best invention of the 20th century. So anyhow, we'll discuss it again. The radar is there in detail in your 7th semester where I shall discuss it. But in CW, continuous wave, because your signal, I told you, maybe analog or continuous, it can be pulse or digital. That you know probably. So here it is continuous wave or analog type of radar as a broadband linear amplifier. So these are the applications. These applications are again there in your 7th sem, so that's why I'm not going to elaborate them here. Just mention their names. And only one problem I want to show it here. In an N-type gallium arsenide gun diode, these are the following things given. Applied electric field is given, device length. Then I told you L, active length, 15 micrometer. Operating frequency, F is given 10 gigahertz. Calculate the negative electron mobility. So I told you Vs, just this formula you have seen. Vs by L equal to, L by Vs, if I say, L by Vs equal to 1 by F, means tau. L by Vs equal to 1 by F, means tau. So that's why Vs equal to Fl. F is given, L is given. So from there, the value of Vs we are getting 1.5 into this. That is a very simple thing. And mu is Vs by electric field. You have read it. Jet pressure has gone through that. Jet velocity by electric field. So Vs value, we got it from here. Electric field value is given in the problem. Just we have substituted and we got the value. And why I have written negative? Because I told you that as mobility, electron concentration decreases, so that's why mu value is negative for gun diode. So that's why I have rather in the problem also probably it is mentioned that calculate the negative. That's why I have marked it negative. So the answer is 5,000 centimeters square per second. And the last problem is a gun diode is working in transit time mode at 12 gigahertz. The domain of charges at 10 to the 7, this is the velocity of the charge carrier which are moving from lower valley to the upper valley. Calculate the length of the device, and can the device work at these two frequencies, which is the mode of operation in each case. So let's see, number one is that the active length. So you know the formula of active length. Actually, L by Vs is tau 0. L by Vs is tau 0 since transit time. So I have written L equal to Vs into tau 0. L equal to Vs into tau 0. Vs is given and tau 0, that is 1 by F. F is 12 gigahertz. So 1 by 12 gigahertz, that I have written. So the value is coming as 8.33 micron. 8.33 micron. And now the second part. Can the device work at 10 gigahertz or 14 gigahertz? Let's see. Because it is operating at the 12 gigahertz. And that mode is called the transit time mode. Even without going through the solution of the second part of the problem, you can tell that it can, if it operates at 10 gigahertz, then that is called quench mode. Because I told you when the frequency is this is called the delayed mode, because when the frequency is lower, means transit time is more than your normal time of is more than transit time, then it's called delayed mode. So frequency will be lower, and in 14 gigahertz, that is called the quench mode. And anyhow, that we have calculated here from frequency 10 gigahertz means T 1 by F. So it is this. The transit time we have already calculated tau 0 in the problem earlier. So transit time is given here. So automatically, from where we got the transit time, from 1 by 12 gigahertz. 1 by 12 into 10, that is your transit time, and that value is 0.08. So as T is greater than tau 0, as I told you, so it is delayed mode. On the other hand, for the second part of the problem 2, or next part, 14 gigahertz. 1 by 14 gigahertz means again 0.0, and now tau 0 is 0.08. So automatically your T is greater than T t, actually tau 0 is greater than t or t is less than tau 0. As t is less than tau 0 means your time taken by the charge period is less, so automatically frequency will be higher. That's why it is 14 gigahertz, and this mode is called your coincident. So I hope that then it is clear to all of you. And now nothing is there from gun diode except this advantage, as gun diode is unipolar device because only one, because we have seen it drain type, so only electrons are the carrier, so automatically it is a very low noise device, because I told you noise mainly comes due to recombination or generation. When electron flows to a semiconductor, from p side holes come to n side, from n side electron comes to p side, they recombine, so that produces noise. But here only one type of charge, like when you go to FET, the same thing you will see. FET is also a very low noise device. And it is simple to fabricate only n layer and then on the two side n class and then metallize, and can operate up to a frequency of 100 gigahertz. That is not advantage, but anyhow, comparing, if you compare with tunnel out, it is an advantage. And disadvantage, if you tell, then the gun diode is very much temperature dependent. That is the problem, because I told you that whenever you apply voltage and you increase the value of voltage or field, then current will start to flow more and more, then automatically heat will develop and temperature rise takes place. So that's why gun diode is very much temperature dependent, and its frequency, the frequency that varies with this temperature, and the value which is there recorded in the book, a frequency shift of 0.5 to 3 megahertz per degree centigrade rise of temperature. Let me see, temperature rises from 30 to 31 degree, 31 to 30. So for every rise of 1 degree, this will be the frequency shift of this. But by proper design, this frequency can be reduced to 50 kilohertz. From 3 megahertz, it can be reduced to 50 kilohertz. But for that, you need some special circuitry, and you can, your range, then the device can operate. And when you want to get the deviation of 50 kilohertz per degree centigrade rise, then the range with which you are, or within which you have to operate, is minus 40 to 70. So these are the disadvantages, and these are all about your gun diode. So now nothing is there after this. So I am going to stop our discussion over here. But before I finish this particular topic on our today's class, I want to ask all of you, and I'm going to ask one by one to some of you, that whether anything is clear to all of you or not. Okay. Actually, here names of all of you are not showing, but anyhow, I'm going to stop presentation. Probably then I can see your name. Yes, now it is coming. Okay, now, okay. Okay, now the thing is that first I must tell you why today attendance is so poor. Only 37, 36 students are there. Who is the seer of the class?
Hello, sir.
Huh?
Hello, sir. I am the seer.
Why attendance is so thin?
Sir, actually, students were confused if you are taking the class or not.
Okay. Now, but one
Yes,
thing you
sir.
will take care, I am telling you, that I shall tell you at the end. Now, Purvasi, you tell as you, so whether it is clear what today we have discussed?
Yes, sir.
Auditro,
Yes, yes, sir.
is it clear?
Yes, sir.
Shubham,
Yes, sir, clear. Because
actually this device is very important. You always, it is not that for your gate exam I am telling, but at the same time, device generally we say is the pillar of the whole subject electronics. The whole subject electronics actually based on this, the particular topic device, because you will find the application of device in analog electronics, in microwave, in your VLSI, in your micro, everywhere you will find the device. So that's why lots of papers are related with device. If you find any problem, please tell me. Don't feel shy. Don't hesitate to ask me. Okay, just one or two more students I want to ask you. Okay, now, Ankita,
Yes, sir. Yes, sir.
any doubt?
No, sir. Clear.
Okay, okay. Aditya, Aditya,
Yes, sir. Yes, sir.
any doubt? Any doubt?
No, no, sir.
Okay.
Sir, I
Okay,
have request, sir.
okay.
Sir, please share these notes, sir.
Okay, one thing you do, you send a request for share. There is some technique. I don't know how our students are sending. So then it will be easy for me that if I click that share button, then automatically it will reach me. But for
Okay,
that, you
sir.
have to send the request to Google Pay, the share. Okay, then I will share. You send it immediately, I will send it. Okay.
So
Okay,
the
so
request is for the
uh,
class recording.
class recording and PPT, everything is available there.
Okay.
Because PPT is there parallelly. My face you will see there, and side by side you will see every slide. Okay, both are there. Then the whole video is there. Anyhow, actually today I do not want to continue much more, so I want to stop over here. So our next class probably will be in next week. I think you know that